Let's unpack this. For centuries, the timeline of technological advancement has felt, well, it's felt pretty fixed, right? You have the printing press, then the steam engine, then electricity, and finally, the silicon chip. But what if we told you that the crucial conceptual leap, that moment the world figured out how to use mechanical logic to process complex information, what if that could have happened almost 1,000 years ago and thousands of miles away from Europe?
That is precisely our mission today. We are undertaking a deep dive into an extraordinary set of sources that examine the high watermark of the Chinese Song Dynasty, which flourished between 960 and 1279. And this isn't just a historical review, it's a deep exploration of a profound counterfactual thesis. The core idea is that this highly advanced medieval civilization was poised both technically and logistically to develop complex mechanical computation, basically the foundation of true deep tech centuries before anyone else.
And the beauty of this analysis, for you, the listener, is that it doesn't rely on any sort of mystical or unknown discoveries. It's not magic. It roots this massive potential leap entirely within the verifiable technological and industrial capabilities that the Song Dynasty already possessed. We're looking at the intersection of their existing industrial scale, their incredibly complex logistics, and just a single achievable conceptual jump.
It requires no sudden miracle. What it requires is a specific, logical reorganization of robust, established technologies. We're talking about bronze, water, and silk. So to really understand the viability of this claim, we have to first firmly establish the historical baseline reality. We need to appreciate just how industrialized, how financially complex, and logistically capable the Song Dynasty actually was.
This deep dive will fundamentally challenge your assumptions about when and where the foundations of computing were truly laid. We are going back to the 11th century to explore how to build the world's first successful, commercially viable analog computer. Here's where it gets really interesting, because to even entertain this idea, we need to properly appreciate the incredible platform this hypothetical computational leap would have occurred on. The sources describe the Song era from 960 to 1279, not just as, a successful dynasty, but as the closest the world came to an industrial revolution before the one that actually happened in Europe hundreds of years later. Now, that sounds like a massive exaggeration, but when you look at the raw data, the historical facts genuinely back it up.
It's not an exaggeration at all. It is simply a recognition of an astonishing historical peak of innovation and large-scale societal organization. The Song Dynasty was a powerhouse. I mean, when we detail the groundbreaking technological achievements that fundamentally redefined state power, logistics, and communication, the Song produced them.
Right, we often list the famous three: the compass, gunpowder, and printing with movable type. But let's take a moment to really understand the scale of their impact during this time. The compass, obviously, enabled far-reaching oceanic navigation, fundamentally altering global trade potential. And gunpowder didn't just appear as a curiosity. It was integrated into siege warfare, into missile technology on a massive scale. It radically changed the balance of military power.
And then there's printing. We tend to focus on Gutenberg in the 15th century.
Of course.
But the Song developed printing with movable type centuries earlier. This was the first true information infrastructure upgrade globally. It enabled knowledge to be standardized and scaled in a way that simply wasn't possible when you're relying on human scribes. It created an intellectual infrastructure necessary to support an advanced society.
And the scale of these inventions implies an even greater underlying industrial capacity, right? You can't just mass-produce reliable compasses or manage the complex chemical refinement needed for gunpowder, let alone print thousands of standardized texts without significant material and manufacturing resources.
Absolutely. And that brings us to the core of the industrial scale they achieved, particularly in metallurgy. This wasn't small-scale artisan production. The sources clearly state that the production of iron per capita during the Song Dynasty was the largest in the world at the time.
Okay, that per capita figure is astounding. It's not just that a large country is making a lot of iron. It means that the average citizen had access to, or was supported by, a higher output of industrial metal than anywhere else on Earth. We're talking about tools, bridges, weaponry, coins. Everything was standardized and built with metal.
And if we want to put a hard number on that, historical data suggests that by the late 11th century, around the year 1078, China's iron production was hitting peaks of 125,000 tons annually.
125,000 tons.
Yes. And to put that in perspective for you, that single number is comparable to the entire iron production of Europe almost 700 years later in the 17th century.
Wow.
So this wasn't just high production, it was a sustained industrial economy.
And to fuel that, they had to have solved the energy crisis that typically throttles early industrial growth. I mean, you can't sustain that level of output by burning forests for charcoal. You'd run out of trees.
And that's where the pre-industrial revolution aspect truly emerges. Fuel. The Song Dynasty pioneered the sophisticated use of mineral coal. This is the crucial precursor technology. They moved away from a reliance on wood or charcoal, which severely limits scale and causes massive deforestation, and they moved toward utilizing coking coal or high-quality anthracite.
So why is coal such a game changer? What does it let you do that wood can't?
For massive iron production, especially in blast furnaces, coal provides two critical advantages. First is sheer heat intensity.
Hotter fires.
Much hotter fires. And crucially, it lets you avoid impurities. When you burn raw coal directly, it contains sulfur that contaminates the metal, makes it brittle.
Right.
The Song engineers figured out ways to process this coal. It's a process similar to how modern coke is made, which allowed them to achieve the high temperatures and consistent purity necessary for producing vast quantities of steel and high-quality iron. This reliance on mineral coal provided the essential sustainable energy base for developing a true factory-based industrial economy. They had the fuel, the metal, and the demand.
And what I want you, the listener, to appreciate here is that the sheer mechanical capacity needed to mine, transport, and process hundreds of thousands of tons of coal and iron year after year. It shows that this society had the requisite managerial and engineering depth to handle incredibly complex mechanical and logistical systems. They weren't just inventing things, they were scaling production into industrialized processes.
And that complexity wasn't limited to physical hardware. It permeated their abstract, high-stakes financial systems as well.
Exactly. Let's shift from the tangible technology, the iron and coal, to the abstract technology of finance and logistics. This is where the challenge really begins for their administrative class. The Song Dynasty created the world's first widespread paper money system known as jiaozi.
This is an astounding leap.
Yeah.
It's conceptually massive. It moves the entire economic foundation away from inherent value, like metal coins, to representational value, a piece of paper guaranteed by the state. It signifies a profound level of social trust and, more importantly for our deep dive, organizational control.
But the invention of paper money is so much more than just convenience. It creates this enormous logistical challenge for the governing state. If a physical piece of paper represents real wealth, you have to manage its flow, you have to ensure widespread acceptance, control regional exchange rates, and, most critically, you have to prevent widespread counterfeiting across a massive, diverse empire.
It absolutely demanded state-controlled systems for complex logistical coordination. And by necessity, it demanded what we would now recognize as state-controlled algorithms. I mean, think about the manual effort involved. Managing a non-physical currency requires tracking its movement between regional centers, ensuring standardized printing and security features, managing inflationary pressures by controlling issuance limits, and reconciling ledgers across vast distances.
This is effectively the first large-scale, high-stakes data handling problem in financial history. It's a problem that, if you solve it poorly, leads to economic collapse, and they solved it well enough to sustain the system for decades.
It required a deep, internalized understanding of organizational and procedural logic. If clerk A in the north receives X amount of jiaozi and merchant B in the south deposits Y amount, the central authority must have a consistent, repeatable, and precise procedure, an algorithm, for reconciling those values and managing the overall supply, even if that procedure was executed by hundreds of human clerks with abacuses rather than a digital chip.
So if we look at this baseline reality, the massive scale of iron production fueled by industrial coal, and the successful management of a non-physical currency requiring these strict, repeatable logistical protocols. It shows that the societal organization, the mechanical expertise, the resource capacity, and the sheer intellectual capacity were all firmly in place. They had solved the industrial scale problem, and they had solved the complex financial logistics problem. They were, in a way, prepared for the next logical step.
Which is computation. The necessity was already there, driven by the size of their economy and the complexity of their financial instruments. They had the engine, the coal and iron, and they had the data problem, the paper money. All that was missing was the processing unit. And what's fascinating here is the conceptual bridge that was just waiting to be crossed. It involves connecting two seemingly disparate technologies: the sophisticated gears and bronze work they used for industry, and the high-tension fibers used for their most luxurious export silk.
So we are talking about connecting the elegant, centuries-old industry of silk textiles to the abstract precision of computational instruction. That's the link.
Precisely. The central counterfactual scenario proposed by our sources is powerful because it uses established Song technology. The what if is this. What if China, with its unparalleled expertise in complex silk weaving, had independently developed the fully programmable mechanical loom 600 years before the French inventor Joseph-Marie Jacquard popularized it in the early 1800s?
Okay, that seems like an enormous leap. Jacquard's loom used punch cards to automate these incredibly complex, reproducible patterns. How could the Song Dynasty have conceptually bridged that gap from weaving a beautiful tapestry to creating a machine that follows stored instructions?
It's a logical evolutionary leap, and it's rooted in the nature of silk weaving itself. Imperial quality silk demands extreme precision and the execution of incredibly long, complex sequences of thread movements. The Song weavers already had manual looms that were highly complex, requiring multiple operators to follow a specific, codified sequence of actions.
So the human operator was the first processor, in a sense. They were following a manual instruction set.
Exactly. The leap is simply mechanizing that instruction set. A programmable loom uses a physical medium, whether it's linked wooden slats, coated pegs, or punch cards, to dictate which threads must be raised or lowered at any given moment. This dictates the warp and the weft. This process is inherently an instruction-based sequence, and crucially, it is a reusable and adaptable sequence. It provides the perfect physical, conceptual template for any instruction-based machinery.
Right. So the moment the song engineers realized that the sequence of holes on a card or the arrangement of pegs on a drum can be repurposed to dictate a sequence of mathematical operations rather than the sequence of weaving operations, the whole game changes.
And that is the conceptual key. Once they had the mechanical template for sequencing operations, the programmable loom, the thesis posits that the immediate technological leap would be to scale that logic up, to scale it up to create the first mechanical analog computer. The logic of mechanical instruction, once understood for weaving, could immediately be repurposed for calculation and data processing, driven by the pressing needs of the Jiaozi paper money system.
This shifts the entire intellectual focus from craft to computation. We are no longer talking about just repeating a beautiful pattern. We're talking about sequencing a process that yields a numerical result.
And this is where the genius of their existing infrastructure comes into play. Critically, this hypothetical computer would not have required an exotic or new energy source.
Right.
The Song Dynasty were masters of hydraulic engineering. Their system of canals and water wheels was everywhere, powering mills, grinding grain, driving bellows for the iron furnaces. The thesis explicitly states the computer would be powered using this existing hydraulic technology.
So no waiting for steam power, no waiting for electricity. This machine could be built and powered using the abundant, sustainable, and already engineered energy source of the 11th century, flowing water.
Yes. The existing infrastructure of canals, water wheels, and bronze casting capabilities provides the entire computational foundation. You take the high-level algorithmic complexity already proven by the Jiaozi paper money system, you combine it with the reliable mechanical power of the water wheel, and you integrate the instructional capability derived from the weaving template. The pieces were all there. They were simply awaiting that final, crucial logical connection between textile complexity and sequential numerical processing.
It's the ultimate aha moment in alternate history, isn't it? Realizing that all the necessary prerequisites were present, simply awaiting the conceptual breakthrough that links sophisticated silk patterns to sequential computational instructions. That is the moment we conceptually move from hydraulic mills and logistical management to processing massive amounts of data in a single conceptual leap.
And think about the physical components. The gears are turning at a steady, reliable speed thanks to the water wheel. The input is a sequence of holes on a wooden slat, representing a mathematical problem. The output is a series of movements that settle into a numerical result. The transition from a programmable loom that creates patterns to a programmable calculator that processes numbers is merely a change in the interpretation of the output, from warp and weft to digits and results. The underlying mechanical logic remains absolutely constant.
Now we have to dive into the nuts and bolt, or I guess the bronze gears and silk threads of this hypothetical 12th century deep tech. This needs to be a truly deep dive for our listener. How exactly would the Song engineers have handled what we call binary logic using purely mechanical means?
Well, we must remember that binary logic, this idea that complex operations can be derived from combining simple on-off or true-false states, it's an abstract concept, not an electrical one. The sources outline that the core principle ties directly back to the physical movement inherent in the weaving machine.
Okay, so let's establish the two-state system. In modern computing, it's voltage presence, which is a 1, or voltage absence, a 0. In this mechanical system, the binary state is provided by the precise, controlled physical position of a component.
Exactly. When you look at the design of a mechanical instruction template, like the pattern drum of a programmable loom, a specific lever must be either pushed, so engaged, or released, disengaged at a precise moment. This physical position provides the necessary two-state system for computational instructions. A lever engaged, allowing a corresponding gear to turn, is the true state. That's your 1. A lever held stationary, preventing movement, is the false state. That's your 0.
So the input, instead of being electrical voltage, is the physical presence or absence of a notch on a barrel, or the physical deflection of a lever, which translates directly into the engaged or disengaged state of the main mechanical processor.
And that mechanism, which is driven by the constant kinetic energy of the water wheel, would manipulate the actual physical processor components. This is computation applied mechanically, where the fundamental logical gates are physical bronze gates, and the flow of information is the timed movement of metal.
Okay, let's talk about building a fundamental logic gate, the true essence of a computer, using the Song Dynasty's advanced bronze casting capabilities. If we were building, say, an AND gate, how would two bronze input levers and a single output rod interact? Let's walk through that.
Right. That requires focusing on interlocking mechanisms. For an AND gate, the output only turns on or becomes A1 if both input A is 1 AND, input B is 1 simultaneously. So imagine two input levers, A and B, and they're positioned to physically block a central bronze output shaft.
Okay, so the output shaft wants to turn because the water wheel is constantly trying to drive it, but it's currently physically blocked by these two levers.
Precisely. Now, if input A is true, A1, the lever corresponding to A shifts out of the way. But if input B is false, A0, the lever B remains in place and the shaft stays blocked. The output is still 0. Only when input A and input B both shift simultaneously, meaning both input signals are true, is the central shaft finally released. The turning of that shaft becomes the output signal, the 1, and that turning shaft can then physically activate the next stage of the calculation.
And that's the essence of cascading logic.
I see. The output from one gate, which is the physical rotation of that shaft, becomes the input for the next series of gates. And the complexity is built by linking these simple bronze mechanisms together, allowing the machine to perform multi-step operations like addition, subtraction, or comparison.
But now a complex machine isn't just one gear. It needs connectivity and synchronization. And this is where the sheer physical size of the machine, which could potentially span a small industrial building, poses a significant problem. How do you reliably transmit the result of a calculation from one bank of bronze gears to the next bank across, say, a 20-foot distance? This is where that elegant, low-tech solution specified in the sources comes in. High-tension silk threads.
Exactly. High-tension silk threads would be used to transmit the mechanical signals. A slight controlled movement by a bronze gear pulls or releases the attached silk thread. That transmits the 10-state, the binary pulse, across the machine to the next computational stage. And the material choice here is absolutely crucial.
But wait, I have to challenge that because this sounds like a major vulnerability. We're talking about computation that requires incredible precision. Wouldn't environmental factors like humidity or just simple material stretch over time immediately ruin the synchronicity needed for accurate calculation?
That is a critical engineering challenge, and it's where the Song Dynasty's mastery of the material really shines. Firstly, these wouldn't be simple, loosely woven strings. We're talking about specialized, high-tensile, multi-filament silk, maybe even chemically treated for stability. And secondly, the computational facility itself would need to be climate-controlled. Remember, the machine is powered by a water wheel, which means it's likely located adjacent to a controlled waterway.
So the engineers would construct a purpose-built structure, maybe with specific internal climate controls and tensioning mechanisms, effectively treating the computational area like a modern clean room, but for mechanical stability.
Precisely. And the high tension itself mitigates stretch. A pull on the silk thread registers as a true state, a 1. If the thread breaks or loses tension due to slack, it registers as a clear mechanical failure, a 0. So it's a built-in error-checking mechanism. It's reliable because they were using an abundant material silk in an extremely high-quality controlled application. It is functioning as a mechanical wire carrying pulses, a low-mass, durable means of signal transmission.
And what ensures the whole massive apparatus runs synchronously, so that one set of gears doesn't finish its calculation before the input signal from a previous set has even arrived?
That is the role of the water wheel, which serves as the system clock. The wheel turns constantly, driven by the steady flow of water from a canal. All gear operations would be synchronized to the rhythm of the water wheel's main shaft rotation. This provides the necessary steady clock cycle, turning the gears at a predictable rate, ensuring that all inputs and outputs across the various banks of logic gates happen simultaneously before the cycle repeats.
So the robustness and the low-tech elegance of the system truly rely on this. Computation achieved without electricity, without reliance on rare materials. It's relying solely on highly sophisticated mechanics, the superb existing metallurgy for the logic gates, and organizational logic applied to flowing water and high-tension silk fiber.
The complexity isn't in finding a new element, it's in the organizational blueprint. The Song Dynasty possessed the engineering skill to execute the hardware, the steady, sustainable energy source to power it, and the conceptual template, the programmable loom to derive the instruction set. They had all the constituent parts to build a complex, multifunctional mechanical calculation engine.
So what does this all mean for the world? We've successfully moved from bronze gears and silk thread to a fully functional analog computer humming along, powered by a river in 12th century China. What is the ultimate application of this technology? Because technology never stays in a lab, it goes where the money is. The sources provide a truly remarkable answer: world-changing wealth driven by computational speed.
The primary application for a machine capable of complex, rapid calculations in the Song Dynasty, a highly commercialized society already managing sophisticated abstract finance, would undoubtedly be transaction processing and financial modeling. The most valuable output would be information advantage.
And the high-value destination proposed is the establishment of the Hangzhou Stock Exchange, a financial hub operating using these new mechanical computers.
And this is more than just a place to trade, this is a system. A stock exchange in the 13th century, built upon high-speed mechanical logic, fundamentally changes the dynamic of regional and international commerce. While modern exchanges deal with stocks and bonds, the Hangzhou Stock Exchange would address the highest value trade of the era.
And what would be the centerpiece of this computational market? What are they trading?
The computers would be used for facilitating the negotiation and trade of futures contracts for major commodities, specifically tea and silk. And this is high-stakes, sophisticated finance, the buying and selling of agreements for massive volumes of goods to be delivered weeks or months in the future, based entirely on predictive market analysis.
Futures trading is intensely computationally demanding. Even today, you need to calculate risk based on weather patterns, predict supply chain bottlenecks along the Grand Canal, factor in geopolitical shifts, and execute trades instantly when a price divergence is detected. This is where the mechanical computer's speed becomes the definitive economic weapon.
That's the crux of the argument. The analysis highlights the sheer speed advantage provided. These transactions would be executed in mechanical milliseconds. Now, while a modern electrical millisecond is orders of magnitude faster compared to a human clerk calculating manually with an abacus, which takes minutes or even hours, a mechanical computer driven by a water wheel is effectively instant.
Let's call it mechanical millisecond arbitrage. So how does that speed translate into the staggering wealth that's predicted?
Well, arbitrage is the instantaneous process of buying a commodity low in one location and selling it high in another, exploiting tiny price differences. In the 12th century, price discrepancies between, say, the Guangzhou market and the Hangzhou market could persist for weeks.
Because the news traveled only as fast as a mounted courier.
Exactly. The mechanical computer eliminates that delay.
So the computer instantly processes all the incoming data shipment arrivals, harvest reports, tax changes, and it calculates the true unified price.
Precisely. If the computer calculates that tea futures are undervalued in Guangzhou by 0.5% compared to Hangzhou, it can execute a purchase and a simultaneous sale in mechanical milliseconds, long before a human clerk could even notice the discrepancy or execute the first step of the trade. That tiny, guaranteed profit is repeated thousands of times per day, 247, limited only by the speed of the water wheel.
The result is an unprecedented level of market efficiency. It eliminates the friction of human calculation, human error, and human slowness. That ability to process and act instantly on information allows capital to accumulate exponentially.
This creates a hyper-accelerated feedback loop. The mechanical speed generates massive profits in Hangzhou, which attracts capital from merchants across the known world, from Japan, from the Middle East. That capital influx demands more physical infrastructure, more iron for new construction, more silk to trade, more tea to harvest, and critically, more jiaozi, the paper money, to facilitate the transactions.
So the computer acts as a turbocharger. The organizational and industrial might that was already present, the coal, the iron, the paper money system, it becomes the physical engine that expands to meet the demands created by the computational speed.
And this leads us directly to the most staggering economic consequence detailed in the source material. This computational acceleration creates an economic acceleration so extreme that the predicted gross domestic product of China in the year 1200 would surpass the entire global GDP of 1900.
That is an almost incomprehensible figure. A society without trains, planes, or electricity generating more wealth than the entire industrialized world 7 centuries later. It forces you to recognize that wealth is fundamentally about the speed of information processing, not just the complexity of manufacturing materials.
The speed of logical processing is the ultimate driver. Furthermore, this efficiency stabilizes the market. By instantly eliminating large, risky price disparities, the mechanical exchange reduces risk for legitimate traders. It makes investments safer and more predictable. This attracts even more foreign capital, which further accelerates domestic production and intellectual migration toward the center of wealth, which is Hangzhou.
And the societal shift will be profound, too. This hyperwealth would necessitate massive urbanization, further driving innovation in logistics, sanitation, and public administration, creating a permanent, insurmountable technological gap between the Song Dynasty and the rest of the world. The mechanical computer provides the logic, but the sheer wealth it generates transforms the entire civilization.
The computer provides the leverage. It's a paradigm shift where technological organization and the speed of logic, rather than just natural resources, become the primary engine of wealth generation. The Song Dynasty had the physical mass, the iron, the coal, and they had the financial pressure from the paper money, but the mechanical computer would have been the accelerator pedal, pushing their society into a permanent state of exponential economic growth.
What an incredible conceptual journey we've taken. We began with the verifiable historical reality of the Song Dynasty, a society that had mastered industrial iron production, mineral coal, and complex paper money logistics. We then tracked this specific conceptual leap, moving from the mechanical repetition of silk weaving to the sequential processing of data using bronze gears and water wheels.
And that entire robust non-electrical infrastructure was then deployed for maximum commercial leverage. The hyper-accelerated futures trading of high-value commodities in the Hangzhou Stock Exchange, which would, hypothetically, have generated economic growth that fundamentally changed the trajectory of human history.
The power of this analysis is its plausibility. It doesn't rely on magic. It argues that the necessary industrial and intellectual foundations were already established. The only missing element was a specific organizational concept, applying binary logic to mechanical motion, and then realizing the economic power of that computational speed.
And that is the core lesson of this deep dive. True technological leaps rely far less on the discovery of exotic new materials like semiconductors or advanced polymers, and far more on the ability to apply abstract organizational logic like binary code to existing, robust, and abundant resources. The Song Dynasty possessed the engineering skill to execute the hardware and the financial pressure to demand the software.
It's a genuinely humbling thought, isn't it? Realizing how close a pre-modern civilization was to unlocking true computational and therefore exponential economic power.
Which leads us to our final provocative thought for you to mull over. Considering the Song Dynasty had all the components necessary for this mechanical acceleration, the power, the materials, and the need, and simply missed the logical combination, what foundational technology that exists in our world today, right now, might we be failing to combine logically? Are we overlooking robust infrastructure, something as common as carbon structures or biological processes, or even the subtle physics of quantum states, that when correctly organized by a new abstract computational logic, could be delaying our own next global civilizational leap? We might have all the bronze and silk we need disguised as something else entirely, we just haven't seen the final pattern yet.